welcome everyone to this Reinforcement Learning Zurich online event. And as always, we would like to thank our sponsors, which is Swiss Re Institute and Rockstar Recruiting, for making this possible. So let me introduce quickly our speaker today, which is Piotr Stanczyk from Google Research. He has received his master and PhD in computer science from the University of Warsaw. And he's now working as a software engineer at Google, focusing on reinforcement learning and machine learning infrastructure. So, Piotr, we are very much looking forward to your talk.
Thanks a lot, Klaus. So just to make sure, I hope you see the slides just right and full screen.
I can see them, yeah.
Okay. So today I would like to talk to you about Google Research Football, which is a novel reinforcement learning environment that we open sourced last year. And that was a joint effort of many people on Google Brain team in both Zurich and Amsterdam location. And the main purpose for open sourcing this environment was to push research on reinforcement learning by enabling many new directions and combining different features of other environments that are available outside. So in general, when you look at reinforcement learning, it can be applied in practice in many different applications like robotics, self-driving cars, control problems. For instance, Google made application to data center cooling, which significantly reduced the cost of cooling data centers. But reinforcement learning has the basic problem, which is that directly it involves interaction with the environment. And in most practical applications, such interaction doesn't really scale, because if you are looking at self-driving cars, you don't want to crash the driving car multiple times before learning how to properly drive. A similar situation applies to robotics. You can have like a number of robots as presented on the picture, but they break relatively easily. Setting them up is time consuming, and also it doesn't really scale that well. If you want to start your experiments from scratch, it takes multiple days to obtain the data and process everything. So that's why in practical applications, games are used for simulating real world, or at least when it comes to research, when you just work on improving reinforcement learning algorithms without looking at specific applications, you don't really care about some practical aspects, so you can just use any kind of task that can be applied to reinforcement learning and try to improve over time. And those environments, like Atari, for instance, is one of the widely adopted environments, but like in general, such approach provides you with challenging setup for reinforcement learning, depending on the environment. Like Atari is relatively simple, but there are other environments like StarCraft that are super hard to solve. It is easy and cheap to test using this environment, and it's also safe because you don't expose yourself to interactions with the real world, and it's easy to scale. You just add more computers. Sometimes it also comes with significant cost if you look at which are fun but expensive to run. The other types of environments are like motion problems or Go or chess. So in case of Atari games, you can solve those problems. And when you look at state-of-the-art reinforcement learning algorithms, such problems are not challenging anymore. And some of the environments are not necessarily optimizing and price directions. There might be non-stochastic, as in case of Atari, which is quite broadly applied algorithms don't necessarily generalize in a proper way, because they are able to just find a single path to solving the problem, but this is really not generalizing the understanding of the environment. They are single agent or like single player, also applies to like Atari games where like there is no notion of two players playing against or cooperative with each other. We open sourced this GRF environment, which provides you flexible complexity that can be adjusted in both like dimensions. There are different types of levels. You don't necessarily have to aim at solving 11 versus 11 setup, but you can like look at like 4 versus 4 at the beginning. Basically, GRF was open sourced last year, and it's similar to FIFA. If you played that game, large agent learns initially to move and dribble and pass, and over time, as it progresses in the training process, it can finally score some goals. But before that happens, of course, he loses the goals, and the first thing that he can learn is basically how to prevent goals from hitting their goal. There is no focus on low-level control, which is the case for DeepMind's soccer, because we wanted to mainly focus on like higher-level strategy and cooperation between players and multi-agent aspects. And the goal of open sourcing is not to beat the baselines. Like, we don't try to build an agent that can compete with humans on playing GRF or FIFA, but the main focus was to push reinforcement learning research. So we wanted to provide an environment that is easy to use by anyone, and it's not as expensive as other environments that has pleasant graphics like Dota or StarCraft. So GRF consists of like 3 main components. The first component is the game engine itself, which is like highly optimized version of open sourced football game. We provide baselines that we can try to beat if you develop new reinforcement learning algorithm and would like to, for instance, publish a paper. The football engine is basically a modification of open source simulation gameplay football, which was open source in 2017. It has OpenAI API with some extensions. So for instance, to enable model-based directions for research, we extended the API with get state of the environment and set state of the environment, which basically allows you to snapshot the state of the game at any point and restore it to that state. And this way, for instance, you can investigate what happens when you execute different types of actions from exactly the same setup. It supports all football rules. It has a number of reinforcement learning features enabling different directions, as I already mentioned. Yeah, we have all the rules. There are by default 20 different discrete actions available in the environment. There are 8 movement directions, so left, right, bottom up, and combinations of those. There is a do nothing action in case you would like to not decide and not change your current behavior. There are 4 types of passing and shot actions. So 1 long pass, 1 short pass, high pass, and shooting. So basically, passing is done towards the player in the direction you are running. So if you are running backward, then the ball would be passed in the direction. Shooting is always in the direction of the goal. So even if you are not facing the goal of the opponent, player will do some dribble and try to shoot. Also, there are 4 actions for dribbling, stopping dribbling, and sprinting, and also stopping sprinting. And those actions are sticky. So once you execute dribble action, you have to disable it later on Otherwise, your player will keep dribbling, and the same applies to shooting. Basically, in the default setup, you control only one player, and the rest of the players is controlled by built-in ruled adjustable difficulty. But you can also change configuration of the setup you are running and do multi-agent configuration, and it is adaptive. So basically you can control 1, 2, or up to 11 players on your team. You can also play against your trained agent. So you can first train your agent in the environment against built-in AI, and then you can give it play yourself. And for that, you can use either keyboard or special controller. The interface that we provide for hooking up different types of players lets you also try playing yourself or challenging your reinforcement learning agents to beat. In terms of rewards, like the default reward that environment provides is upon scoring. So when you score the goal, you get 1 point. When you lose the goal, you get -1 reward. But as you can imagine, losing the goal is not necessarily that sparse, because if your agent doesn't really know how to defend, events of losing goals will be happening relatively frequently. However, in terms of scoring, it's not the case anymore, because by executing random actions at the very beginning, once RL agent doesn't really understand what is the goal of the game, it's really hard to score. So for that reason, experiments and results that we provide in the paper involve 2 types of rewards. One is the standard reward, the other is shaped reward, which gives additional points for advancing with the ball on the field. So closer to the opponent's goal you are with the ball, more reward you get. And that gives some information to the agent, what is basically the goal of the game, and significantly simplifies the training process. And you can come up with your own rewards, like giving additional points for passing the ball, or for ball or ownership. And basically, as you can expect, it's not that easy to define well-behaving reward function, because if, for instance, you end up giving points for ball ownership, then reinforcement learning agent can come up with strategies that are not necessarily scoring, but he tries to hide the ball away from the opponent, maybe relatively close to the goal of his own. And basically the probability of scoring from such a scenarios is even lower than with standard rewards. So yeah, there is like the reward shaping research is also interesting direction in theoretical RL. Then, depending on the type of agent you train, you can use different representations of observations. We can use raw pixels. So basically you get by default 1280 by 720 stream of pixels representing entire screen. And as you can imagine, training from such data is relatively hard because input is very big. And also agent has to understand all the dependencies between pixels on the screen. So you could try to downsample that. But in practice, what is being used instead of raw pixels is minimap representation, which is basically a smaller version and in 2D. So it's like 2D projection of the 3D view, involving entire field, and players on both sides, as well as the ball, are just marked with a pixel in this representation. And it's relatively good performing for convolutional neural networks. As you can imagine, like those networks have ability of understanding structures in pictures, and turns out that it's also relatively good in solving football-like problems. On top of minimap representation, there is also stacked minimap representation, which allows you to train with networks that are not necessarily LSTM-like, so they don't have to have a memory module. And that way, for instance, using that representation, we can train MLP models with similar performance as LSTM, but that model is cheaper to train. And stacked representation is basically 4 recent frames of the environment snapshotted. There is also floats representation, which consists of floats encoding positions and speed vectors of all players, as well as the ball. And for some reason, this is another direction for research. This representation doesn't really train that well as minimap, and that might be surprising in a way, because minimap representation is bigger, so floats are more compressed form in a way, but still doesn't really train that well with different types of algorithms. In terms of performance, environment allows you to execute up to 140 million steps per day on a single hexacore machine when you run around 10 instances of the environment. And as you will see in the next slides, like different baselines require like 50, 100 million steps. So we are able to solve the big problems, the benchmark problems, in about a day from scratch. And if you try to apply even faster. So in terms of benchmarks and academy, football benchmarks allow you to compare different RL algorithms. And in the paper that we published, we provide baselines for IMPALA, PPO, and DQN. So you can compare your research progress against those. And I guess others that would be publishing on top of the environment. And you are solving 11 versus 11 classical football game, which consumes, and that translates, if you think about the real game, if you played the environment yourself, each step engine of the game renders 100 steps of physics simulation per second. So basically there are 10 physical simulations performed per action done by the agent, and 3,000 steps translate into 5 minutes of gameplay. But if you are not watching the game or playing interactively, then physics engine and the entire environment runs full speed on your machine, achieving higher rate than 110 steps per second. And there are 3 different levels of difficulty, which are also described in the paper, so you can like compare easier or more hard scenario depending on your progress of research. Then we have Football Academy, which provides you with a diverse set of tasks that you can try to solve, and they consist of different difficulty levels. The simplest one is basically scoring the goal against an empty goal without a goalkeeper with relatively short distance. So such a scenario can be solved from scratch with not very strong RL agents in a matter of like few minutes. But then over time you can try more complex tasks. And yeah, here we have some scenarios that are available. So on the top left, there is run to score. Unfortunately, due to the need of moving slides last minute between different computers, animations are gone. But basically what you have to do in the first scenario is to learn to run, because if you end up attacking the goal without executing running action, then your opponents will take over the ball because they will catch up with the player. Then on the top right, we have 4 versus 2 setup, which is counter-attack kind of scenario. You have like only goalkeeper and 1 defender in front of you to tackle. Bottom left represent pass and shoot. So basically, the yellow player on the top of the screen has to learn to pass the ball to the one in the middle of the field in front of the goal, and that one shoots. And the last scenario is a corner kick. Then we have results for our different scenarios as presented in the paper. So as you see, even with 1 million steps of the environment, empty goal close, the simplest scenario can be solved practically in 100% score rate. Then empty goal, in this case, player starts in the middle of the field. Million steps gives you about 80% accuracy. And algorithm wasn't tuned for these cases, so if we adjusted accordingly the training rate, for instance, to reduce the noise at 1 million steps, I guess the score would be even higher. So you should be able to quickly solve those problems. And there are a number of interesting behaviors that we observed with AI. And for instance, consider a scenario of 1 versus 1, where you have to score the goal. What would you do as a human? So most likely you would try to attack the goalkeeper, trying to lob or just shoot from a distance once goalkeeper leaves the goal and gives you some window for taking the shot. But RL agent, again, maybe there will be a video after all. Yeah, hopefully you can see the animation. What reinforcement learning agent came up with is to run with the ball and force a goalkeeper to do a throw-in. Someone has to do it, and that leaves the goal empty, and it's way easier to score against an empty goal with 100% success rate. So this is a strategy, like a winning strategy, that gives you like perfect scoring versus whatever you would come up with as a human. And during development of environment, we noticed a number of bugs, like engine was getting stuck because player couldn't do a free kick due to some reasons. And early stage training was exposing these kind of bugs in the environment because agent wanted to prevent losing goals. So he was trying to make the environment freeze in a way, and we had to fix those issues. So in terms of research directions, here we have yet another video, which I will also provide link to after the presentation. But during 2019-2020 academic year, we had 2 University of Warsaw student groups that were working on the environment, and those teams were focused on 2 directions. One of the teams was working on single agent focus. The other was multi-agent track. And for single agent, they were working on different observations performance, and one of the things they were looking at was to understand why the floats representation is way more complex to solve than the minimap. They also spent time tuning PPO, which is relatively state-of-the-art algorithm that provides you reasonable step complexity. And they also experimented with different ways of increasing difficulty of built-in AI during training to accelerate the training speed. So you can think of it as your agent tries to learn at the very beginning against first graders, and over time, as it understands the game a little bit, we advance the opponent. Multi-agent team, on the other hand, was focusing on controlling all players on the team. And for instance, if you consider a scenario of like 3 players on your team facing directly goalkeeper, so like being close to the goal, if you try to solve this with a single agent, you can obtain up to like 75% accuracy, because sometimes when you perform a shoot action, you just miss the goal or goalkeeper takes the ball from you. But when you control all 3 players in the scenario, then they can perform a synchronized tactic, which allows you to pass the ball between them once the goalkeeper tries to approach the player with the ball, and then perform a shot which has like which is guaranteed basically. And there is a link to the blog post which contains a number of graphs and descriptions of the experiments. So it's a nice read that you might be interested in looking at. If you are interested in giving this environment a try, then there is a GitHub repository, Google Research/football, which contains all the instructions and all the links to different resources. You can install environment on your local machine or using Docker image. You can also use a collab, so it's like the quickest way of giving environment a quick try. Unfortunately, within the collab setup, you are not able to render nor play yourself, so it's only about like looking at 2D rendering of the game and trying some ideas. But also, it might not be the right way of doing end-to-end training of your agent, which takes substantial amount of time for more complex scenarios. And here we have a simple example of using environment. You can create environment just providing name of the scenario you want to run, and this 11 versus 11 stochastic is the default one that play game script also uses. So this is basically the thing that by default you would play if you wanted to do it yourself. And then you just use a standard gym-based API for advancing steps on the environment and obtaining observations and rewards. Then another interesting thing that is worth looking at is CDRL, which is a reinforcement learning framework that we open sourced last year. And it provides baselines, like there is a paper and it compares our original paper of GRF to what you can obtain with CDRL, and CDPro enables you to do distributed training of your agent on Google Cloud using GPUs and TPUs, and it significantly speeds up hold time training compared to IMPALA algorithm described in our original paper, up to like 80 times, given a high number of actors taking part in the training. And the main advance compared to IMPALA algorithm is that both training of the model and inference happens on the accelerator in the centralized learner node, so that it's cost efficient and low latency. Learner contains a batching layer, so as you can imagine, like both GPUs and TPUs require significant amount of data to process in one go to be efficient. And so the batching layer groups a number of observations from different actors to process and generate actions. And once it has a full batch, it dispatches this operation to the TPU or GPU and sends the actions to the actors back for executing on the environment. Details can be found in the paper. Another thing is the Google Research Football Kaggle competition that was launched last month in cooperation with Manchester City. And as of today, we have over 9,000 teams participating. And this is the best way of like comparing your agent against others participants. There are a number of rule-based models written by hand, as well as trained agents. So not only you have to compete with reinforcement learning, but also whatever different contestants came up with as the rule-based solutions. And with that, we are almost in time, just 2 minutes over. So hopefully we have some time for questions, if there are any.
Yeah, great. Thank you very much, Piotr, for this very fascinating talk. Really cool. Yeah, so for everyone online, you can ask questions, you can write the questions under Q&A. So Piotr, I was wondering about the Kaggle competition. Do you already, can you share some, let's say some results or some insights? Is there anything interesting? Have you analyzed it a little bit, what's going on there?
So the rules of the competition don't allow us to look into the solutions of the contestants. Only the winners are publicly sharing their solutions. So we don't have like the insights of what is happening under the hood, unfortunately. But from like discussions, there is like reinforcement learning solutions are not widely discussed. However, there is a lot of talk about defining strategies for rule-based agents, and like people define ways of computing if a given player is open on open position, and the ball can be passed to him, and such things.
So you think this is competitive, the rule-based approach?
Well, it's for sure competitive, given that solving like playing against built-in AI in the first place, and this built-in AI is also rule-based, the one provided with the environment. It like requires for the hard setup 500 million steps for V-trace algorithm. So yeah, it's definitely, you can make it challenging. Also, when you look at, for instance, FIFA, there are different levels of opponents, and of course, human players are better than built-in AI in football, but you have to train for quite some time to beat the most strong opponents. So yeah.
Maybe you see there is one question here in the chat.
So you have previously said that the stacked minimap representation enables the use of NLP models without memory models in them. Which particular models would be a good fit for this setting? So basically, in case of minimap representation, we tried a couple of convolutional neural networks, and those worked well. We didn't like the project of open sourcing the environment wasn't focused on trying out different types of algorithms and networks, because we wanted to provide an entry point baseline for other researchers to solve, and we focused on like enabling different research directions. So yeah, those things are to be tried, I would say.
And there's one question like Q&A. Maybe I missed this part in the presentation, but does GRF support self-play?
Yes, so self-play is supported through this multi-agent and multiplayer mode. So basically what you can do is to start your training by playing against built-in AI. And once you have something trained, you can just swap or even hot swap opponent that you play against, which is built-in AI, with your trained agent. And you can do that for a single player that controls the ball on the opponent team, or you can even control all 11 players on the team. So it can be mixed of self-play, multi-agent by itself, and all possible variations.
It seems there are no more questions. Yeah, so then we thank you again, Piotr. Thank you very much.
Thanks a lot for listening.
Yeah.
And staying with me.
So maybe we will look at the Kaggle competition. And so everyone, thanks for joining. Yeah, nice to see so many of you. Yeah, have a nice evening and see you next time.
Thanks. See you. Take care.
Bye-bye.